Hi. In this video, I'd like to talk some more about the equilibrium constant K. So far, we've spent some time defining it and calculating it, but now I'd like to spend some time talking about how to use it and why it's useful. In a nutshell, it allows you to find the quantities of substances that will be present when a reaction reaches equilibrium. So that's clearly has a wide array of applications. So I'm going to give you one example of that today, and some general remarks as well. Okay, so the exact value of K is given by this formula, as we've discussed. RT ln K is equal to the negative Gibbs energy of reaction at standard state. And for gases, that's the example I'm going to be doing. For gases, we saw that K is equal to the ratio of the partial pressures of the products over the reactants at equilibrium. And you can find an explanation for all of this on page 113 of these lecture notes. Okay, so looking at this equation in the box, let's make some observations. First of all, if this reaction Gibbs energy is positive, since there's a minus sign, that means the left-hand side must be negative. So RT ln K must be negative. However, R and T are both positive, always. Therefore, the ln K is the only part that can make it negative. Therefore, this implies that K must be less than 1, because that would give us a negative natural log. Conversely, if the reaction Gibbs energy is negative, then RT ln K must be positive. And these numbers are always positive, and so that means the ln K must also be positive, which would imply that K must be greater than 1. So this alone already tells us something. These quantities can be computed for a given chemical equation using the Gibbs energy of formation values in a table. And by computing these values, we will get an idea of whether K is less than 1 or greater than 1. So we're going to use that in the example that we're going to do. And another thing that I want to point out is that for gases, we have this value for K. So let's see what this implies for those partial pressures. All right, so K is this fraction for gases. So if K is less than 1, that would imply that the denominator is bigger than the numerator at equilibrium. And if the partial pressure of A is greater than the partial pressure of B, that would imply that A is favored, meaning there will be more of it than B at equilibrium. And A is the reactant. So if K is less than 1, the reactant is favored. And we can run through a similar argument for K greater than 1. If K is greater than 1, then that means the numerator is bigger than the denominator at equilibrium, which means that gas B is favored, which means that the product is favored. Okay, so several useful conclusions that we can draw based on the value of K. And we at least know whether K is greater than 1 or less than 1 based on this value. And furthermore, we can calculate K exactly using this equation. So to summarize everything that I've said so far, if this reaction, Gibbs energy, is greater than 0, then that implies that K is less than 1, which implies that the reactant or the reactants is favored at equilibrium. And the Gibbs energy of reaction is negative, then K is greater than 1, which means that the product is favored. Okay, and next I'd like to define a new term, the degree of dissociation. It's given the symbol alpha, and it's equal to the fraction of the reactant that has decomposed. All right, so in symbolic terms, alpha would be the initial amount minus the final amount divided by the initial amount. So the fraction that has decomposed. The initial amount is going to be larger than the final amount since this is decomposing. The number of moles is decreasing, so this is going to be a positive number. Okay, and now I'd like to work an example. Since we've been talking about gases, then the example I'd like to work involves gases. This is the decomposition of water vapor into H2 and O2 gas. And so the question that we could answer is, well, first of all, we can calculate the standard Gibbs energy of reaction, and that works out to be 118.08 kilojoules per mole, and that's at a temperature of 2300 Kelvin. And now we can let this reaction progress to equilibrium and ask, what is the degree of dissociation of the water once equilibrium has been reached? So what is alpha at equilibrium? And we're given that the pressure in this case is 1 bar. All right, so since we're going to equilibrium, then when equilibrium is reached, the number of moles final, as we had it written in the formula for alpha, is going to be the equilibrium value. Since we're going all the way to equilibrium, the final value will be the equilibrium value. So that means alpha, and yeah, I'll leave it in initial unchanged. So that means alpha looks like the initial, minus the equilibrium value over the initial value. Okay, so the first thing we're going to do is find the exact value for K, which we can do because we know delta RG standard and we have the temperature. So using the formula that we've seen before, the natural log of K is going to be negative delta RG standard over RT, all of which are numbers that we have. So plugging them in, this works out to be 6.1750, which means that K is e to this number, which is 2.081 times 10 to the minus 3. And remember, K is dimensionless. There are no units. Okay, the next step is that we want to find the initial and final expressions for the initial and final number of moles for each of these species using the chemical formula here, the chemical equation that we have. Okay, so the first thing is, what are the initial amounts? And here we're assuming that we start with water and nothing else. And then we wait for this to go to equilibrium, and we want to see how much of the water has decomposed. The next thing we'd like to fill in this table is how much will each of these change in order to reach equilibrium. And for that, we can use this chemical equation. But first, it's helpful, instructive to consider what is N final going to be for water, which is the same thing as N equilibrium. So looking back up here in my formula for alpha, I can solve this for N equilibrium. And what do I get? I multiply the initial I over, I have to add and subtract, so I end up with the initial minus alpha times the initial. So, or I can simplify that to the initial times 1 minus alpha. So going down here, I can right away put this in here. If the initial is n, then the final is going to be n times 1 minus alpha. And that's basically just by using the definition of alpha. We haven't really done anything extraordinary here. We've just used the definition of alpha to write in an expression for the equilibrium value in terms of the initial value and alpha. Now, by comparing these, we can see how much did this need to change in order to equal this. Well, before I factored this, it was n minus alpha n. And we started with n and we ended with n minus alpha n, then the change must have been minus alpha n. Okay. To put that another way, this plus this should equal this. Okay. Now, if H2O decreases by an amount, alpha n, how much does H2 change? Well, the stoichiometric coefficients are the same, and so H2 is going to increase by the same amount that H2O decreased. And O2, the stoichiometric coefficient is a half, so it's going to increase by a half as much as the H2O decreased. Okay, so we got these. Basically, we got these two from the chemical formula, the chemical equation, I mean, and we got this one from the definition of alpha, which gave us this. Now over here, we can add these together to get the final amounts of H2 and O2. So 0 plus alpha n and 0 plus 1/2 alpha n. All right, so I tried to summarize this a little bit. So we used this, which came from the definition of alpha, to get this quantity. And once we had this quantity, then we use the stoichiometric coefficients to get this quantity and this quantity. And then we add the first two rows to get the third row. And now that we have these amounts, we can write the total amount at equilibrium. Total amount at equilibrium is going to be the sum of these. So I'm going to expand this again. So I have n minus alpha n for this one, plus alpha n plus 1/2 alpha n. And you see that the minus alpha plus alpha n cancel, and I'm left with n plus a half alpha n, which I can factor out the n, and I have n times 1 plus half alpha. So this is the total amount at equilibrium. So once I know the total amount, and I know the individual amounts, I can use those to get the mole fraction. Okay, so I'm now going to calculate the mole fraction for species J at equilibrium. And that's going to be the next row in my table. And this mole fraction is going to equal row 3 divided by this. Okay, so it's going to equal n equilibrium for species J divided by n total. Okay, I put in some grid lines to try to make this table a little easier to read. All right, so now I'm going to take row 3, which is my equilibrium value for each of these, and divide by this total number of moles to get the mole fraction, x. Okay, so I have, for this one, it's n times 1 minus alpha divided by n total, which is n times 1 plus half alpha, and the n's cancel. Next one is alpha n divided by same total, and the n's cancel again. And then the last one, 1/2 alpha n over the total, and again, the n's cancel. All right, and one more row, I'm going to find the partial pressures of each of these gases in their equilibrium stage. So to do that, I'm just going to take the mole fraction and multiply by the pressure. Right? This is a formula for partial pressure that we saw all the way back in chapter 1. So I'm just going to take each of these and multiply them by P. All right, and there we go. So we've completed this table, and this last row is going to be the useful one and what's next. All right, so remember that K can be found from the activities. In this case, it would be the activity of H2 raised to the 1 times the activity of O2 raised to the 1/2 divided by the activity of H2O raised to the 1. And remember that for gases, we could estimate the activities using the partial pressures. Okay, and so I'm going to make this substitution over here, and I'm going to drop the, I'm going to not drop the partial, the standard pressure, but I'm going to include it in my quantity. I'm going to write a single quantity for this fraction here, just to make this a little bit cleaner. So let me call this PJ, I'll put a bar over it, okay? So K then, I'm taking each of these A's and I'm replacing it with PJ bar. So I have PH2 bar times PO2 bar to the 1/2 over PH2O bar. All right, and then the next step is to take these values for the partial pressures that I calculated in terms of alpha and plug them in down here, okay? So one at a time, we've got the partial pressure of H2, which is this one. So that's alpha P over 1 plus 1/2 alpha times the partial pressure of O2, which is this one, 1/2 alpha P over 1 plus 1/2 alpha to the 1/2, divided by the partial pressure of H2O, which is this one. So I'm going to multiply by the reciprocal of this, and I have 1 plus 1/2 alpha over 1 minus alpha P. Okay, so we're done with the table, so I moved it out of the way, and now let's make some simplifications. First of all, I see this 1 plus 1/2 alpha and 1 plus 1/2 alpha. I've got 1 in the denominator and 1 in the numerator, so those are going to cancel. And next, I'm going to combine the alphas together. So I have alpha times alpha to 1/2, so that's alpha to the 3/2. And I'm going to combine the p's. So that's p times p to the 1/2, so p to the 3/2. And I also have 1 over root 2. So I'm going to put the root 2 in the denominator, 1 over root 2, times alpha to the 3/2 p to the 3/2, where p is the pressure in our problem, which was stated in the beginning to be 1 bar. So we'll make use of that in just a minute. And then that's it for the numerator, and then I still have these terms down here in the denominator. So I have 1 plus 1/2 alpha to the 1/2 times 1 minus alpha times p. All right, a couple more simplifications I can do. This p to the 3/2 divided by p, I can simplify, so this p will cancel, and this 3/2 will become a 1/2. And another thing I can do is I'm going to move this root 2 inside of this square root. So I've got a square root times a square root, right? The product of 2 square roots is equal to the square root of the product, right? So I can put the 2 inside. So that leaves me with, on the bottom, the 2 comes in, and I get 2 times 1 plus 2 times 1/2 alpha, all still square rooted, times 1 minus alpha. Okay, that's about all the simplifications I can make until I use some further assumptions. So backing up to the problem statement, here is delta Rg standard. It was given to us, 118 kilojoules per mole, okay? A big positive number. And backing up to the summary that we had for gases, if I have a positive number, then I know that the reactant is favored in equilibrium. And in this case, I have a very large positive number. So the reactant is going to be very favored at equilibrium. So if the reactant, which in this case is H2O, is very favored in equilibrium, what do we expect the final alpha to be in equilibrium? Well, remember that alpha is the degree of dissociation, and if the reactant, which is H2O, the thing that's dissociating, is favored in the equilibrium state, then we expect alpha to be very small. Very little of it will have decomposed. So we're gonna take advantage of that assumption. Okay, so I've summarized that here. Since this is so much larger than 0, we expect the reactant, which is H2O, to be heavily favored in equilibrium, which means that alpha will be small, meaning that not much of the H2O will have decomposed. Okay, so now we're going to utilize that assumption. If alpha is small, let's say much less than 1, then we get some simplifications up here. 1 minus something that's much less than 1 is approximately 1. And 2 plus something that's much less than 1 is approximately 2. So the denominator here simplifies to just root 2. So my formula for K now looks like this. And K is known. We calculated it exactly at the very beginning. P is given. P is 1 bar. And so now we can solve for alpha. We know everything here except alpha. We can solve for alpha. Okay, and I should have carried my bar through here all along with the P's. But since P is 1 bar, then this P bar, which was P over P standard, is going to be 1 over 1. So P bar is 1. So this number is just 1 to the 1/2. And solving for K, then, or solving for alpha, then I just multiply the root 2 over and take the 2/3 power, and I get this formula for alpha. And again, we know K. We calculated it exactly at the beginning of this problem. So plugging in the value for K, we get 0.0205, which means only about 2% of the H2O has decomposed at equilibrium. Okay, so far when we've been working with gases, we've been using partial pressure as our estimate for the activity. But what if we wanted to do that in molar concentration instead of partial pressure? Maybe we don't have this kind of data. Maybe we're dealing with concentration values instead. So this is the last case I'd like to go through for section 6A. All right, so the perfect gas law, P equals nRT over V for species J. And this is equal to Nj over V, the number of moles of the gas over the volume, is the concentration. So I'm going to write that as concentration of species J, RT. So this is just the perfect gas law. Okay, and then I'd like to return to the definition of K. So remember K was equal to the product over all of the species involved of their activities raised to their stoichiometric number. And these are the equilibrium values of A, which when we first wrote this definition, I put equilibrium as a subscript, but that's usually not included because we know if we're talking about K rather than Q, then we're assuming we're talking about equilibrium values. Now we can use our estimate for the activity of a perfect gas being the partial pressure to rewrite AJ as the partial pressure of J over standard pressure to the new J. And now I'm going to plug in my perfect gas law, which is in terms of the molar concentration. So PJ is going to be the concentration of J, RT, over P standard to the new J. Okay, so just rewriting this down here, And this is a product of many terms, and the order of operations when you're multiplying doesn't matter. So I can break this product up into the product of two products, okay? So that's what I'm gonna do. And I'm gonna group things in a convenient way. So the first is I'm gonna take the molar concentrations, I'm gonna multiply all those together first, okay? And then to that, I'm gonna multiply everything else. So I'll have RT over P to the new J. All right, and now I'm going to both divide and multiply by C standard, that's the standard concentration, which will set to 1 mole per liter. And actually, I'm going to multiply and divide by C standard to the new J so that I can put the C standard inside of this power to the new J. So this term looks like this, where I've got the concentration to the new J over the standard concentration to the new J, which is what I divided by. And over here, I'm multiplying by the same quantity, so I haven't changed the value of the overall product. All right, and then this term right here, I'm going to give it a special name. I'm going to call this Kc, the equilibrium constant in terms of concentration. That's why Kc. And now I can write this as Kc, so K equals Kc times this product. Okay, so here's how we defined Kc. And I want to point out that this is a dimensionless quantity because I have concentration divided by concentration, which was the motivation for dividing and multiplying by standard concentration up here. So like the other equilibrium constants we've seen, Kc then is dimensionless. And now I'd like to focus on this second part that is multiplied to the Kc. So if you look at this, everything in here, none of it depends on J. Inside the parentheses, nothing depends on J. So when we do this product, we're going to be doing this to the new 1 times this to the new 2 times this to the new 3, right? Only this is changing with respect to when J changes. So I'm going to expand this product for a few terms so you can see what's going on. So the first term of the product is going to be this to the new 1. The second term is going to be this to the new 2. The third term will be to the new 3, and so on until we've gone through all of the J's. And here we just have the product of the same base with different exponents, which means we can take this base and raise it to the sum of the exponents. Okay, so we have this to the sum of all of the new values of new J, and the sum over J. And actually, I'm going to call these new A, new B, new C, because that's how we label species, is with letters. And then I want to point out that this, which equals new A plus new B plus new C, etc., we're going to call this delta nu. And why delta? That's because it's, remember, the nu for the products are positive and nu for the reactions are negative. So that means it's basically the sum of the products coefficients minus the sum of the reactants coefficients. So that's the justification for calling it delta nu. Okay, so gathering this all together, we end up with the equilibrium constant is equal to this concentration equilibrium constant times this quantity raised to the delta nu, which is the sum of all the stoichiometric coefficients, or the stoichiometric numbers. And notice that inside parentheses here, I have P standard, which is predetermined. I have C standard, which is predetermined. We already gave these values. We said this was 1 bar, and we said this was 1 mole per liter. And we have R, which is a constant. And so we can compute this part of it, at least, in advance. P standard over C standard times R is 12.03 Kelvin. All right, so now this formula simplifies to the temperature divided by 12.03 Kelvin to the sum of the stoichiometric numbers. So this is a pretty useful formulation for finding K. If you know the temperature and you know the chemical equation, then you can figure out what this is equal to, no problem. And Kc is defined in terms of the concentration. So if you know the concentrations, then you can find K, or vice versa. If you know K, which again, we can calculate K using delta Rg. If we know K, and this can be easily calculated, and then Kc, we will have the concentrations to solve for. So this is one last example for section 6A.